Hello everyone, in this video I'll be talking about NMR spectroscopy, Proton Nuclear Magnetic Resonance, as there are several types of NMR spectroscopy such as Proton NMR spectroscopy, Carbon NMR spectroscopy, nitrogen, fluorine, and several other NMRs. So in this video exclusively I'll be talking about Proton NMR spectroscopy, and I'm following the book Clayden chapter 11. From that chapter I'm going to I have taken notes from that chapter, and I'll be talking through completely from that chapter only. I'm not touching other books for this lecture, but I'll be making more videos for the NMR from other books as well, like such as Pavia Introduction to Spectroscopy, Silverstein, and LG Wade and Jenai Simit. So I'll be making more videos about NMR from those other books, but in this video exclusively I'll be talking about NMR spectroscopy from the Clayden book. Okay, let's start. So what we will discuss in this chapter is Proton NMR spectroscopy. Proton NMR compares with Carbon NMR. So we will do comparison with Proton and Carbon, and then we will discuss how coupling in Proton NMR provides most of the information needed to find the structure of an unknown molecule. And then we will discuss the using Proton NMR with other spectroscopic methods to solve the structure rapidly, and using Proton NMR to investigate the detailed shape stereochemistry of molecules. And then Proton NMR spectroscopy is referred to in most chapters of the book as it is the most important for determining structure. You must understand this chapter before reading further. Okay, what we usually need for characterization of any molecule is these three prongs. One is carbon 13 NMR spectroscopy, infrared spectroscopy, and mass spectrometry. And along with that, we would require Proton NMR spectroscopy to confirm the structure of any given molecule. So Proton NMR and Proton NMR are interchangeable terms. Sometimes people write this H NMR, and sometimes people write Proton NMR. They are same things. Chemists often use proton to mean not only H plus but also the nucleus of a hydrogen atom forming part of a nucleus. As you know that hydrogen contains one proton, that's why it's called proton, or sometimes it's called H NMR, and 1 indicates the atomic number of hydrogen, and that is 1, or 1 indicates the number of protons present in the hydrogen, and it's only one proton present in the hydrogen. That's why we write it H1, and also we call it Proton NMR because it just contains one proton. This is how it will be used in this chapter. Okay, that was the clarification why we call it Proton NMR and why we write it H1. An instance where Proton NMR was not useful, so it's not always that Proton NMR will be excellent, but in most of the cases Proton NMR gives very useful and information regarding the structure, elucidation, and characterization of the organic compounds. In chapter 3 you met methoxetin, chapter 3 of the Clayden book. Okay, Proton NMR has little to tell us about its structure as it has so few protons. It is C14H6N2O2, that's the molecular formula of this methoxetin. Carbon NMR and eventually an X-ray crystal structure gave the answer. Yesterday I made a video about drawing crystal structure and introduced the XRD of the single crystal XRD as well. So ultimate characterization of any molecule is single crystal structure, but not all of the compounds are capable of giving us crystal structures, they do not crystallize. So we should always rely on the Proton NMR as well. So but in this case there are 4 OH and NH protons best seen by IR and only 2 CH protons. The later protons are that kind that Proton NMR reveals best. Fortunately, most of the compounds have lots more than this. So all of these organic compounds contains hydrogens and carbon network, and they can easily be characterized through Proton and NMR spectroscopy, but sometimes IR spectroscopy is more helpful, and sometimes mass spectrometry is more helpful. So if we combine all of these 4 techniques, IR spectroscopy, mass spectrometry, proton and carbon, and with the 2D NMR as well, so we should be able to find out what is the structure of the compound. Okay, let's move on to the differences between carbon and proton. So we used the C13 NMR in chapter 3 as part of a three-pronged take on the problem of determining molecular structure. Important though these three prongs are, we were forced to confess at the end of chapter 3 that we had delayed the most important technique of all, Proton NMR, until a later chapter because it is more complicated than C13 NMR. This is the delayed chapter and we must now tackle those complications. We hope you will see Proton NMR for the beautiful and powerful technique that it surely is. The difficulties are worth mastering. For this is the chemist's primary weapon in the battle to solve structures. So Proton NMR differs from carbon NMR in a number of ways. Number one is proton is the major isotope of hydrogen, that is 99.985% natural abundance, while C13 is only a minor isotope, that is 1.1%. And the Proton NMR is a quantitative. The area under the peak tells us the number of hydrogen nuclei, while C13 NMR gives strong or weak peaks from the same number of C13 nuclei. So in simple words, we can integrate the Proton NMR, we cannot integrate the carbon NMR when we are discussing the differences of proton and carbon. The third difference between proton and carbon is protons interact magnetically coupled to reveal the connectivity of the structure, while C13 is too rare for coupling between C13 nuclei to be seen. Proton NMR shifts give a more reliable indication of the local chemistry than that given by C13 spectra. We shall examine each of these points in detail and build up a full understanding of Proton NMR spectra. The other spectra remain important, of course. Proton NMR spectra are recorded in the same way as C13 NMR spectra. Radio waves are used to study the energy level differences of nuclei, but this time they are proton and not C13 nuclei. Hydrogen nuclei have a nuclear spin, so this is the basic. The energy of the number of energy levels available to a nucleus of spin is 2I plus 1. That's the formula. So this is the basic principle of the NMR spectroscopy. So if you have a lower energy level and you have a proton there, and then if you supply energy, it goes to higher energy, and applied magnetic field is in the direction of energy. So nucleus aligned with applied magnetic field, nucleus aligned against the magnetic field. So that's the first diagram. You should understand it. And so we continue from this. Hydrogen nuclei have a nuclear spin of a half and so have two energy levels. They can be aligned either with or against the applied magnetic field. The spectra look much the same. The scale runs from right to left, and the 0 point is given by the same reference compound, though it is the proton resonance of Me4Si rather than the carbon resonance that that defined the 0 point. You will notice at once that the scale is much smaller, ranging over only about 10 ppm instead of the 200 ppm. So in carbon NMR we have a ppm scale from 0 to 200 and even 0 to 230, but in proton we usually have a scale from 0 to 10 or sometimes 0 to 16 or 0 to 14. This is because the variation in the chemical shift is a measure of shielding of the nucleus by electrons around it. So NMR measures the electron density surrounded by the nucleus around the nucleus. There is inevitably less change possible in the distribution of 2 electrons around a hydrogen nucleus than in that of the 8 valence electrons around a carbon nucleus. Here is a simple NMR spectrum. So this is how NMR spectrum looks like. So this is the Proton NMR spectrum of acetic acid, and the OH, the hydrogen of hydroxyl group of acid appears most downfield and deshielded at around 11 to 12 ppm, and the methyl group of the acetic acid appears at around 3 ppm, and we have an internal standard that is tetramethylsilane. And carbon is, this is a proton spectrum, so carbon will not be observed and oxygen is not also will be observed. So in proton only protons are observed, and this is a delta sign, and these values are called ppm, that is parts per million. So this is a typical proton NMR spectrum. So integration tells us the number of hydrogen atoms in each peak. So the another information that we get from proton NMR spectrum is how many hydrogens are giving signal to correspond to the given peak. So the chemical shift of the 12 hydrogen atoms of the 4 identical methyl groups in tetramethyl is defined as 0. The methyl groups in the acid is next to the carbonyl group and so slightly deshielded at about 2 ppm, and the acidic proton itself is very deshielded at 11.2 ppm. The same factor that makes this proton acidic, the OH bond is polarized towards oxygen, also makes it resonate at low field. So far things are much the same as in carbon NMR. Now for a difference, notice that the ratio of the peak heights in this spectrum was about 3:1. So if you can see, the height of this hydrogen is smaller compared to the height of this signal of protons. So the more the number of hydrogens, the height will be longer. Higher will be the length of the signal, and smaller the number of hydrogens, lower will be the length of the signal. So as this signal corresponds to 3 hydrogen, that's why its height is 3 times more than compared to this red hydrogen that is belonging to OH group. 3:1, and that is also the ratio of number of protons. In fact, it's not the peak height but the area under the peak that is exactly proportional to the number of protons. Proton spectra are normally integrated, that is, the area under the peak is computed and recorded as a line with steps corresponding to the area like this. It is not enough simply to measure the relative heights of the peaks, because as here some peaks might be broader than others, hence the area under the peak is measured. So for example, that is Proton NMR spectrum of acetic acid. So we are measuring area under the peak, not the height. So area under the peak is 0.75 centimeter, and whereas for this one the area under the peak is 2.25 centimeter. So from this we can calculate the integration, and this signal corresponds to 3 proton and this signal corresponds to 1 proton. Simply measuring the height of these steps with a ruler gives you the ratio of the numbers of protons represented by each peak. Knowing the atomic composition from the mass spectrum, we also know the distribution of protons of various kinds. Here the heights are 0.75 and 2.25 centimeter, ratio of about 1:3. The compound is C2H4O2. So since there are 4 hydrogen atoms altogether, the peak must contain 1 times hydrogen and 3 times hydrogen respectively. That's how we do structure elucidation in the proton NMR spectroscopy, and this is how integration helps us to understand how many protons are corresponding to the particular peak. In the proton spectrum of 1,4-dimethoxybenzene, there are just 2 signals in the ratio of 3:1. This time the compound is C8H10O2, so the true ratio must be 6:4. A sign in the spectrum requires the same attention to symmetry as in the case of C13 NMR spectra. For example, that is the proton NMR of 1,4-dimethoxybenzene, and this is the carbon NMR of 1,4-dioxybenzene. As you can see, there is a clear difference in the both type of techniques. The proton NMR ranges from 0 to 10 or 0 to 14, but carbon NMR peak scale goes from 0 to 220 or 0 to 200. And if you can see that the ppm values are higher in carbon NMR and ppm values are lower in proton NMR. And if you look at the proton NMR, and don't forget that every NMR spectrum is recorded in some sort of a solvent, and that solvent should be deuterated, and all NMR solvents should be deuterated, because if we do not use if we use simple solvents without deuteration, then they also contain protons and they will be observed in the NMR spectrum, and then it will be difficult for us to find out which peak belongs to signal and which peak belongs to your compound. And because the spectrum, the range of the proton NMR spectrum is very low, so it's from 0 to 14, so the signals of the solvents will also appear at the same region where the signals of your compound will also be there, so there will be a huge overlapping and it will be messy. So to avoid this situation, one must always use the deuterated solvents. All deuterated solvents are available, like deuterated DMSO, deuterated acetone, deuterated chloroform, so on, deuterated benzene as well. So this peak here at 7.2 corresponds to deuterated chloroform, and this signal, which is around 6 to 7 ppm, belongs to the benzene protons attached with benzene. As you can see, this structure is symmetrical, so we should see one signal for the benzene and one for the methoxy groups, as there contains 2 signals for methoxy, but we should have a different integration for the 2. This group, this signal which is belonging to this protons of the methoxy group, should correspond to the integration of 6 protons, as there are 2 methoxy groups, and this signal should correspond to 4 hydrogens, as there are 4 hydrogens present in the benzene. And it's a symmetrical, but if you look at the carbon, we observe 3 carbons, and that is a different story, as we are not discussing the carbon NMR in this video. But I'll be making more videos related to NMR, where I'll be discussing carbon NMR, depth NMR, noisy NMR, cozy, HMQC, HMBC, head core, and all other things later on. So in this next example, it is easy to assign the spectrum simply by measuring the steps in the integral. There are 2 identical methyl groups, CME2 having 6 hydrogens, one methyl group by itself having 3 hydrogens, the OH proton 1H, the CH2 group next to the OH 2 hydrogens, and finally CH2 group between the oxygen atoms in the ring. That's the one which we discussed here. So if you look at this one, you have a chloroform as a solvent. We do not consider this one as a peak, and we have a very tiny peak and it's very broad. We should assign these peaks to this OH group, and these are the hydrogens which are greenish in color. They should correspond to 4 hydrogens, and the height should be bigger. And there are orange CH2 and CH3. So one should be, this one is similar in height compared to this one. So this should be CH2 and this should be CH3. And there are a couple of methyl groups which correspond to 6 hydrogens, and they are black in color. That's the one. So this is how you can integrate the signals and get information from the proton NMR spectrum. So proton NMR spectra are generally recorded in solution in the deuterated chloroform, that is CdCl3. So D is another isotope of hydrogen. That is a chloroform with 1 proton replaced by 2H. So the proportionality of the size of the peak to the number of protons tells you why, if you ran a spectrum in CHCl3, you would see a vast peak for all the solvents HS, because there would be a much more solvent than the compound you wanted to look at. Using CdCl3 cuts out all extraneous protons. So regions of the proton NMR spectrum, the integration gives useful, indeed essential information, but it is much more important to understand the reasons for the exact chemical shift of the different types of protons. In the last example, you can see one marked a similarity to carbon spectra. Protons on saturated carbon atoms next to oxygen are shifted downfield to a larger ppm value, here 3.3 to 3.9. The other regions of proton NMR spectrum are also quite similar in general outline to those of C13 spectra. Here they are, the regions of the proton NMR spectrum. This is tetramethylsilane, which is at 0, and protons on unsaturated carbons next to oxygen. These are the aldehydes. Protons on unsaturated carbons, benzene aromatic hydrocarbons, they appear from 6.5 to 8.5. Protons on unsaturated carbons such as alkenes, so the signals for alkenes appear from 4.5 to 6.5, and signals for saturated CH3, CH2, CH next to oxygen, they appear from 3 to 4.5, and the signals for saturated CH3, CH2, CH not next to oxygen, they appear from 0 to 3 ppm. So this is a really important table for understanding the ppm values for the NMR spectrum. Okay, let's move on. These regions hold for protons attached to carbon. Protons attached to oxygen or nitrogen can come almost anywhere on the spectrum. Even for CH signals, the regions are approximate and overlap quite a lot. You should use this chart as a basic guide, but you will need a more detailed understanding of proton chemical shifts than you did for C13 NMR chemical shift. To achieve this understanding, we now need to examine each class of proton in more detail and examine the reasons for particular shifts. It is important that you grasp these reasons. An alternative is to learn all the chemical shifts off by heart, not recommended. So you should not memorize the chemical shifts, not at all. This is not going to help you at all, but you should understand them, why we are observing these protons at 3 ppm, why we have some signals at 6, why we have some signals at 5. So there is a reason, there's a concept behind that. In this chapter, you will see a lot of numbers, chemical shifts, and differences in chemical shifts. We need these to show that the ideas behind proton NMR are securely based in fact. You do not need to learn these numbers. Comprehensive tables can be found at the end of the chapter 15, which we hope you will find useful for reference while you are solving problems. Again, do not attempt to learn the numbers. The second two compounds, dichloromethane and chloroform, are commonly used as solvents, and their shifts will become familiar to you if you look at a lot of spectra. You have seen sigma used as a symbol for chemical shift. Now that we have two sorts of chemical shift in the C13 and spectrum and the proton spectrum, we need to be able to distinguish them. Sigma means chemical shift in the proton NMR spectrum, and sigma carbon chemical shift in the carbon NMR spectrum. So protons are unsaturated carbon atoms. Chemical shifts are related to the electronegativity of the substituents. We shall start with protons unsaturated carbon atoms. If you study table 11.1, you will see that the protons in a methyl group are shifted more and more as the atom attached to them against more electronegative. So for example, effects of electronegativity: if we have a lithium which has electronegativity of 1.0 and the compound is methyl lithium, the ppm value will be minus 1.94. As you can see, lithium is very electropositive element. It's a metal, so metals shift the spectrum to upfield and shielded region, so the signal appears in the -1. Next is silicon. So the electronegativity of silicon is 1.9, and if you see here which is tetramethylsilane, so the ppm value is 0.0, and if we attach nitrogen which has electronegativity of 3.0 in case of methyl amine, the ppm value will appear for methyl group is at 2.4. If we replace nitrogen with oxygen, the electronegativity will become 3.4, and the example of this compound is methanol, and the methyl group of methanol appears at 3.5 ppm value. If we replace oxygen with fluorine, the electronegativity of fluorine is 4.0, and the methyl group of methyl fluoride appears at 4.27 ppm. So as you can see, as the electronegativity increases, the signal tends to appear at downfield at higher ppm value. So higher the electronegativity of the attached atom, the higher will be the ppm value. Okay, that's the concept you should have in your mind. When we are dealing with simple atoms as substituents, these effects are straightforward and more or less additive. If we go on adding electronegative chlorine atoms to a carbon atom, electron density is progressively removed from it, and the carbon nucleus and the hydrogen atoms attached to it are progressively deshielded. For example, if you see here, there are 3 hydrogens, there are 2 hydrogens, and there is 1 hydrogen. So if you see the proton NMR shifts when we have 3 hydrogens, then the proton value is 3.06, and we have 1 chlorine. And if we add 2 chlorines, the signal will appear at 5.30. And if we add 3 chlorines, the signal will appear at 7.27 ppm. As you can see, the electronegativity effect is additive. So as you add more electronegative atoms, the ppm value changes, and more the number of electronegative atoms, higher will be the ppm value. But if you can look at the C13 NMR spectroscopy, where similar trend is observed, when we have 1 chlorine, the signal appears at 24.9. When we have 2 chlorine atoms, then the signal appears at 54.0. And when we have 3 chlorines, the signal appears at 77.2. So clearly there's a huge impact of electronegativity over the chemical shift. So proton chemical shifts tell us about chemistry. The truth is that shifts and electronegativity are not perfectly correlated. The key property is indeed electron withdrawal, but it is the electron withdrawing power of the whole substituent in comparison with carbon and hydrogen atoms in the CH skeleton that matters. Methyl groups joined to the same element, say nitrogen, may have very different shifts if the substituent is an amino group, has say over 2.41 ppm, or a nitro group has 4.33 ppm. A nitro group is much more electron withdrawing than an amino group. What we need is a quick guide rather than some detailed correlations, and the simplest is this: all functional groups except very electron withdrawing ones shift methyl groups from 1 ppm, where you find them if they are not attached to a functional group, downfield to about 2 ppm. Very electron withdrawing groups shift methyl groups to about 3 ppm. So here is another interesting table that will guide you to pick the ppm values. So approximate chemical shifts for methyl groups: no electron withdrawing functional groups, methyl at about 1 ppm, aromatic rings, alkenes, alkynes. Less electron withdrawing functional groups: X, methyl X at about 2 ppm, add 1 ppm. Carbonyl groups: acids, esters, ketones, nitriles, amines, sulfides. More electron withdrawing functional groups: methyl group at about 3 ppm, oxygen based groups: ethers, esters, amides, sulfones. So this is how you can broadly classify where your methyl group will appear in your NMR depending upon where the methyl group is attached. Rather than trying to fit these data to some atomic property, even such a useful one as electronegativity, we should rather see these shifts as a useful measure of the electron withdrawing power of the group in question. The NMR spectra are telling us about the chemistry. Among the largest shifts possible for a methyl group is that caused by the nitro group, that 3.43 ppm, at least twice the size of the shift for a carbonyl group. This gives us our first hint of some important chemistry. 1. Nitro group is worth 2 carbonyl groups when you need electron withdrawal. You have already seen that electron withdrawal and acidity are related, and in later chapters you will see that we can correlate the anion stabilizing power of groups like carbonyl, nitro, and sulfone with proton NMR. Methyl groups gave us information about the structure of molecules. It sounds rather unlikely that the humble methyl group could tell us much that is important about molecular structure, but just you wait. We shall look at 4 simple compounds and their NMR spectra, just the methyl groups, that is. The first 2 are the acid chlorides on the right. These are the 2 acid chlorides, and one contains 3 methyl groups and the other one contains 2 methyl groups. Rotation about single bond is generally very fast. You are about to meet an exception. Rotation about double bond is generally very slow. It just doesn't happen. This was discussed in chapter 7. So the first compound shows just one methyl signal containing 9 hydrogens at ppm value of 1.1 ppm. That's the first compound. This one contains 3 methyl groups, and 3 times 3 is 9. So every methyl group contains 3 hydrogens. So 3 methyls will contain 9 hydrogens. So this tells us 2 things. All protons in each methyl group are the same, and all 3 methyl groups in the terbutyl group are the same. This is because rotation about C bond, about the CH3C bond and about the CH3C bond is fast. Though at any one instant the hydrogen atoms in one methyl group or methyl groups in the tertiary butyl may differ, on average they are the same. The time averaging process is fast rotation about a sigma bond. The second compound shows 3 signals, one at 1.19 ppm and one at 2.17 ppm. That's the second compound. These 2 methyl groups are not identical. As you can see, one appears at 1.99 and another one appears at 2.17. Now rotation is slow. Indeed, the carbon double bond does not rotate at all, and so the 2 methyl groups are different. One is on the same side of the alkene or cis, the carbonyl group, while the other is on opposite side or trans. The second pair of compound contains the CHO. This is the aldehydic group. One is simple aldehyde, the other an amide or formic acid. It is DMF. So first one is DMF. DMF stands as organic solvent, that is dimethyl formamide. The first has 2 sorts of methyl groups, this one, but this is not the DMF. Okay, this is something else, but DMF is dimethyl formamide, but very similar to this one. So the first has 2 sorts of methyl groups, this one, one appear at 1.81 ppm for the SME group, and a 6 proton signal for the CME2. The two methyl groups in the 6H signal are the same again because of first rotation about single bond. As you can see, this is the DMF, which contains two methyl groups which are non-equivalent, and as they are involved in resonance or rotation around the carbon-nitrogen single bond. The second compound also has two methyl signals at 2.89 and 2.98 ppm, each 3 hydrogen, and these are the two methyl groups are nitrogen. Restricted rotation about the NCO bond must be making the two methyl groups different. You will remember from chapter 7 that the NCO amide bond has considerable double bond character because of conjugation. The lone pair electrons on nitrogen are delocalized into the carbonyl group. The chemical shifts of CH2 group. Shifts of the same order of magnitude occur for protons on CH2 group and the proton on CH group, but with the added complication that CH2 group have two other substituents and CH group 3. A CH2 methylene group resonates at 1.3 ppm, about 0.4 ppm further downfield than a comparable CH3 group 0.9 ppm, and a CH methine group resonates at 1.7 ppm, another 0.4 ppm downfield. Replacing each hydrogen atom in the methyl group by a carbon atom causes a small downfield shift, as carbon is slightly more electronegative, 2.5 ppm, H is equal to 2.2 ppm than hydrogen, and therefore shields less effectively. So chemical shifts of proton in CH, CH2 and CH3 group with no nearby electron withstanding groups. So CH appears at 1.7 ppm, it's downfield by 0.4 ppm value. CH2 appears at 1.3 ppm and methyl group appears at 0.9 ppm. So the upfield signal is for CH3 and the most downfield signal is for CH2 and CH, and CH2 is in middle. This is the benzylic CH2, which appears approximately at around 3 ppm. This is a phenylalanine amino acid. The benzylic group PCH2 is very important in organic chemistry. It occurs naturally in the amino acid phenylalanine, which you met in chapter 2. Phenylalanine has its CH2 signal at 3 ppm and is moved downfield from 1.3 ppm mostly by the benzene ring. Amino acids are often protected as CBZ in carboxybenzyl by reaction with an acid chloride. So this is the amino acid which reacts with CBZ, benzyl chloroformate. Here is a simple example together with Proton NMR spectrum of the product. Now the CH2 group has gone further downfield to 5.1 ppm. Whoa, as it is next to both oxygen and phenyl. So this is the CH2 group, which is in between oxygen and phenyl group, and it appears at 5.1 ppm. That's the NMR spectrum of this one, and the signal for these black hydrogens is this one, which is at 5.1, and this a tiny broad spectrum corresponds to this NH, and this the orange signal is for carboxylic acid, which is at 11.2, and the benzene signal appears at around 6 to 8 ppm, and these red methyl groups appear at 1 point something ppm. So the reason why we are discussing this NMR, because we discussed that the CH2 groups appear at 1.3, but if we change the electron density around the CH2 group, then the properties or the chemical shift value will also change, hence the product will also be different. The chemical shift will also be different. That's why we have a CH2 unit appearing at 5.1 instead of 1.3. Like double bonds, cage structures prevent bond rotation and can make the two protons of CH2 group appear different. There are many flavoring compounds from herbs that have structures like this. In the example here, myritinol from the myrityl bush, there is a 4-member ring bridged across a 6-member ring, the CH2 group. This is myritinol aldehyde, and this one is 2.9 proton, and this one 4. And the methyl appears at 1.33 and this methyl appears at 0.74. And the bridge has two different hydrogen atoms. One is over a methyl group, this one, and other one is over the enol system. That's the one. No rotation of any double bond in the cage is possible, so these hydrogens are always different. and resonate at different frequencies 1.04 and 2.49. The methyl groups on the other bridge are also different for the same reason. Chemical shifts of CH groups. A CH group in the middle of a carbon skeleton resonates at around 1.7 ppm, another 0.4 ppm downfield from CH2 group. It can have up to 3 substituents, and these will cause further downfield shifts of about the same amount as we already seen for CH3 and CH2 groups. Here are 3 examples from nature. Nicotine, the compound in tobacco that causes the craving though not the death, which is doled out instead by the carbon monoxide and tars in the smoke, has one hydrogen atom trapped between a simple tertiary amine and an aromatic ring at 3.24 ppm. This one, we're talking about this one. And then we have a lactic acid. That's the lactic acid, methyl ester of lactic acid. Lactic acid has a CH proton at 4.3 ppm. This one. You could estimate this with reasonable accuracy by taking 1.7 for the CH and adding 1.0 for carbon plus 2.0 for OH equals to 4.7 ppm. Vitamin C ascorbic acid has 2 CHs. One at 4.05 ppm is next to an OH group estimate, and one next to a double bond and an oxygen atom at 4.52, and this one is 4.52 and this one is at 4.04 of ppm. So as you can see from this slide that the ppm value shifts towards the downfield at the higher values when it is in between the electron withdrawing groups. So in the previous slides we discussed the ppm value for methyl and CH2, and now we discuss the ppm value for CH groups. So as you can see, an interesting case is the amino acid phenylalanine, whose CH2 group we looked at a moment ago. It also has a CH group between the amino and the carboxylic acid groups. If we recorded the proton NMR spectrum in D2O, either in basic NaOD or acidic DCl solutions, DCl or HCl, so DCl is a deuterated version of the hydrochloric acid, and NaOD, sodium deuterated oxide or sodium hydroxide, is a deuterated version of NaOH solution. We see a large shift of that CH group. In basic solution, the CH resonates at 3.60 ppm, and in acidic solution at 4.35 ppm. There's a double bond effect here. This is acid group and this is NH3 positive, are both more electron withdrawing than carboxylate anion and NH2. So both move the CH group downfield. Phenylalanine, DCl D2O, that's the 4.35 ppm, and NaODA and D2O, that's 3.60 ppm. So D2O, NaOD and DCl have to be used in place of their proton equivalents to avoid swapping the spectrum with H2O protons. All acidic protons are replaced by deuterium in the process. More on this later. Use your simple guide to chemical shifts. We suggest you start with a very simple and therefore oversimplified picture, which should be the basis for any further refinements. Start methyl groups at 0.9 methylenes, CH2 at 1.3 and methynes, CH at 1.7 ppm. Any functional group is worth a 1 ppm downfield shift except oxygen and halogen, which are worth 2 ppm. This diagram summarizes the basic position. So if you have a CH unit, it should appear at 1.7. If you have a CH2, it should appear at 1.3. If you have a CH3, it should appear at 0.9. But if CH is attached with oxygen, halogens, nitro or amides, then add 2 ppm value into 1.7. And if CH2 is attached with this, then add again 2. And if CH3 is attached with these oxygen, halogen, nitro, then again add 2 for this as well. But if CH, CH2, CH3 are attached with alkene, aryl, carbon and nitrile sulfur, then add 1 ppm to their parent number. This is a very rough and ready guide, and you can make it slightly more accurate by adding substituents, subdivisions at 1.5 and 2.5 ppm, and including the very electron withdrawing groups nitro, ester, fluoride, which shift by 3 ppm. This gives us a summary chart on this page. which we suggest you use as a reference. So these are the alkenes which shift by 1 ppm, alkynes, nitrile, carbonyl, thiol, sulfide, includes aldehydes, ketones, acids, esters, amides, to be added to 0.9 for methyl, 1.3 for CH2 or 1.7 for CH. Shift of 1.5 when includes benzene or heterocyclic pyridines, aryl ring AR, amine NH2 sulfoxide is this one, and shift by 2 ppm when it is attached with OH group, OR group, amide group, halide group or sulfone, and shift by 2.5 ppm if it is aryl ether, shift of 3 ppm if it is attached with nitro, ester or fluoro. Answers deduced from this chart wouldn't be very accurate but will give a good guide. Remember, these shifts are additive. Take a simple example, the keto ester below. There are just 3 signals and the integration alone distinguishes the 2 methyl groups. From the CH2 group, 1 methyl has been shifted from 0.9 ppm by about 1 ppm, the other by more than 2 ppm. The first must be next to carbonyl and then second next to oxygen. More precisely, 2.14 ppm is a shift of 1.4 ppm from our standard value of 0.9 ppm for a methyl group, about what we expect for a methyl ketone, while 3.61 ppm is shift of 2.71 ppm close to the expected 30 ppm. As you can see, this is a methyl ketone and a methyl ester. So the methyl of this ketone appears at this position and methyl ester appears at this one, and the CH2 is in between 2 electron withdrawing group, which is this one, and we have deuterated solution, which is chloroform. So as so far we discussed the chemical shift changes by adding the electron withdrawing groups to the CH3, CH2 or CH, and higher the electron withdrawing nature of the group, higher will be the ppm value for that, and the signal will shift will be moved towards downfield. And with that, I am going to end this video here, and thank you for watching, and I'll be continuing with the chapter of NMR spectroscopy in the next video as well. So it's a very big chapter in the Clayden book. Clayden is organic chemistry, excellent book, and I'm following that book. And this chapter is NMR chapter, and we will be discussing more about NMR in the next videos, and I'll be following the same chapter from the Clayden. Thank you, take care, bye, see you.